light comes in, you can start.
Yeah.
That, huh? Okay.
Yeah.
I'll mute myself.
Yeah. So I'm going to start now. So thank you, Bhaktos, for arranging this talk. And today I'll talk about metal-insulator transition in three-dimensional and two-dimensional systems. And so this transition are actually different type of transitions. And let's see actually what type of transitions are there in day-to-day life. And you see that today is actually the transition from the day, the DPS seminar is actually transferred from the day to a night shift. So this is just one type of transition. And also Google Meet is actually free to pay. So, but I'm going to talk actually the metal insulator transition today. And I'll go back to few weeks. So where actually Bhakto started actually his presentation saying that zero third phase transition during in actually the vanadium oxide V2O3. He was talking about the spinodal instability during the transition. And today, so if we see, so what does it mean actually a metal insulator transition? A metallic system behaves like actually if you go down with the temperature, its resistivity or its resistance actually will go up. It is the insulating character. And if you see, if you go down the temperature, its resistance slowly increases. And towards very low temperature, its value is quite high. Whereas if you decrease the temperature, for a metallic sample, the resistance decreases. And in this context, in V2O3, and in the room temperature or in the around 200 Kelvin or room temperature, the resistance is around something 10 ohm. As soon as you reach around 150 Kelvin, there is a phase transition. And suddenly the resistance becomes actually something 10 to the power 5 or 10 to the power 6, which is actually overall actually 5 order change in its resistance at the transition temperature. So this type of transition, metal to insulator transition, whereas in the previous in the high temperature, in the high temperature it was metallic. Sorry. So it was in the metallic. So with a 150, it becomes actually insulating. So as there are many students are there, if you would like to actually have a metal insulator transition, any review, you can go through this review of modern physics, which is by Imada, Fujimori, and Tokura, and there are a lot of examples and lot of models, and it is a very well explained review of a review article. And I suggest that these people can actually go through this RMP to have actually more and better knowledge about the MIT. So let's talk actually the metal insulator transition in general. And MIT is actually one of the highly studied subject in CONMAT. And this MIT you can achieve by mostly in the 3 ways. One is by actually if you change the composition. That means if system, let's actually you have a system A, and you can dope with another element B, then it can change from the metallic to insulating, or it can change from the insulating to metallic. And there are several models which explains this MIT. And one is actually a strong localization, which is called Anderson localization. And this can also explain the MIT. And even if the formation of the impurity band because of the doping can also explain this MIT. Whereas if the doping can generate a strong Coulomb interaction, then also it can lead to a mode transition with a satisfying mode criteria, and it develops actually a split. It is split actually the conduction band into actually a filled lower Hilbert band and the fully empty upper Hilbert band, and this can explain AMIT. And also the population theory can also explain AMIT. This actually happens when actually you change the composition X. Whereas if you change the temperature, then also you can actually achieve this MIT. So the crystal can actually have a phase transition, whereas in the V2O2, in VO2, you can have actually two different crystal phase. The crystal phase is here, it is something different, and here it is actually is different. So you can achieve a crystal phase transition by MIT, and also weak localization can also tell you and can also explain your metal-insulator transition. And there is another transition called the Pales transition, or the charge density wave transition, which can also make a metal to insulator. And mostly in this metal-insulator transition, it develops a gap at the Fermi energy. And like even if it is a crystal phase transition, you have a band gap of band gap of the hard band gap. And in the Pales transition also you will have a gap because it's the insulating phase. But in superconductivity, though it actually develops a gap, but it is not actually going to a insulating state, but it is going to a superconducting state. But Pales transition also develops a gap, and superconductivity develops a gap, but this is the difference in the superconductivity. And also, if you actually apply pressure, then also you can go for one phase to another phase, which can shift from a metallic to insulating. And Gautam is actually working a pioneer in this pressure, high pressure studies, which actually gives actually two different phases. So let's actually, I'll talk actually as a parent compound of the WO3 is actually tungsten. Let me pick up a three-dimensional system. So with a WO3 is actually three-dimensional system, you can dope many alkali metals. If you put actually lithium, sodium, potassium, rubidium, cesium. So with your alkali metal, the crystal structure changes, different hexagonal, then tetragonal, 1, 2, then it goes to actually cubic. And also with a different concentration, the different structure develops with a single alkali metal. So we have actually, out of this lithium or alkali metals, more studied alkali tungsten bond is actually your sodium doped, because it reaches actually the cubic phases, which is actually more easier to actually understand and develop actually models to understand the metal insulator transition. And let's see actually why though all alkali metal doping should behave in a similar way, why actually for the higher atomic number elements are actually crystallizes in the hexagonal, whereas for the smaller lithium like sodium, they goes towards actually cubic. That is the first question one should ask, and we have actually explained actually in this way. So let's say for sodium, the ionic radius is actually 0.95 Armstrong, whereas if you do it in the cubic structure, the cubic channel is actually 0.96 Armstrong. So sodium can actually fit well with this channel, and this one is actually your octahedral, and this is just like actually you have a cubic crystal with a sodium at the alkali metal at the center, and you have a octahedral at one corner. I mean the oxygen oxygen is around the the BO6 octahedral at the oxygen at the corner, and this B atom is actually in the W is actually in the center of this octahedral. So if you put, and let's see actually the potassium and rubidium and cesium, their ionic radius is actually much more than the sodium, which cannot be accommodated in cubic. So that is why it goes to actually a hexagonal structure and it stabilizes there. So that is why if I go back, so sodium and rubidium and cesium are actually crystallizes in a hexagonal more stability, and as you reduce the atomic radius, then it becomes actually it stabilizes in the cubic phases. So let's see what actually its band structure says. You have a cubic crystal structure in a WO3. In a WO3, and because WO3 is a band insulator, this valency band is actually fully occupied, whereas this conduction band is fully unoccupied. As soon as you put actually sodium reduces actually this tungsten W6 to a lower oxidation phase, and it gives back its sodium 3s electron to tungsten 5d, and any amount of sodium doping that electron will go to tungsten 5d conduction band, and the system should be actually behave like a metallic. So let's see actually how it would be. In a WO3, you have you have your Fermi energy is actually inside the gap, and as soon as you put a electron, in a NaWO3, the electron will go to the tungsten conduction band and it will become metallic. So the conclusion is, if you in a WO3, if you put sodium, whatever the X, the system should behave like a metallic from the band picture. That was the initial our feeling. So but when we dope sodium and measure its resistivity, we found that for a small part of the sodium, though for 0.05, it should be actually metallic, but its resistivity says that it's actually insulating. This insulating feature continue up to 0.25, and for the larger X value, it actually shows actually metallic feature. That means there is a metal-insulator transition somewhere in the 0.25 composition. So that is actually origin. That what's the model actually, which model is actually appropriate to explain this metal-insulator transition occurring with the doping. So let's actually understand what are those models in little bit more detail. So if you dope sodium, so sodium can go inside the crystal randomly, and this random distribution of sodium plus ions gives rise to a strong Brigadier effect, and as a consequence, Anderson localization occurs in the conduction band tail, and all these states are actually localized, and you have a critical edge of this strong localization. If your EF lies below your critical edge, the system is insulating. As soon as if you put more and more sodium, your EF will move upward, and as soon as it crosses your critical edge, it will become metallic. Expansion by the Anderson localization. Whereas impurity band also can explain your MIT. What happens? Your EF can actually lie inside the impurity band, where that impurity band is actually localized, and in the gap, your EF is actually false, and you have a metal-insulator transition. When you have a EF here in this impurity band, you will have a metallic character, whereas it crosses, then it will have a insulating character because there is no density of states. But you should have actually different of the impurity band, and this type of impurity band you can see in semiconductor with a very lightly doping electron doping material. Or you can have actually Mott transition. What happens if you are doping, if you are putting actually sodium in the WO3, and this S electron is going to 5d, and 5d become a very strongly correlated electrons now. So they repel each other, and the system becomes very correlated, and it can satisfy a Mott criteria, which is actually the bandwidth can be actually equivalent to a your Coulomb repulsion, and it will actually split the conduction band into sub band, lower Hubbard band, and the upper Hubbard band. And the lower Hubbard band can be fully occupied, and EF can lie actually in the gap, and you can have actually metal to insulator transition. But for that, you need actually a very strong correlation that you can actually study later. Or you can check the percolation theory can also explain a metal-insulator transition. Let's this pink color is actually your WO3. As soon as you put actually sodium any amount, that becomes actually sodium NaWO3. NaWO3 is metallic, and this blue becomes actually NaWO3, and this becomes actually cluster of NaWO3 spread over your WO3 matrix. As soon as you put actually, you increase your sodium concentration, you may get actually a channel which is actually going from one end to other end, and when you do resistivity, it gives actually a conducting path, and the system can behave like a metallic. So for this, but this implies that you have actually metallic phase, and also insulating phase. So let's actually first validate this, whether actually this population theory is actually right or wrong in context of the sodium tungsten bronze. So then you have to do actually a special type of spectromicroscopy experiment. What does it mean? You can do actually a photo emission spectroscopy, and you can collect a spectra and you see that as a microscopy, and your spot size has to be sub-micron. That means if the spot is actually falling on this pink subject, it will give you a insulating feature, whereas if its spot is falling on this blue, that will give actually a metallic feature. By that way, you can say that its inhomogeneity is actually there inside the sample, and the percolation theory can well explain your metal-insulator transition. So with this, we want to actually focus our studies, and so we have taken 3 samples. One is actually a very lightly doped WO3, and a 0.7 and 0.8 are the very metallic compositions. And a system of 0.8 and 0.7 should give actually a high density of states as Fermi energy because they are metallic, whereas a low doping sodium WO3 is actually insulating, should give actually a 0 density of states at the EF, which actually insulating. And but if that means if the population theory is right, then at some part you'll see a 0 density of states in a spectra in a same sample, whereas in some position it can be a metallic spectra. So let's see what it says. In a insulating sample, we have taken you have taken in different spots, and in every spot the spectra is same, but the mapping shows actually a different yellow and red type of patches. These are actually artifact of the spectra. That means the spectra is not well focused in red zone, whereas it is well focused in the yellow zone. Because when we clean the surface, and actually we don't clean, actually we fracture the sample, and the fracture sample is not actually very like, though it is clean and it is some steps are there. So that's why you can see those steps as artifact in the spectromicroscopy images. So but surprisingly, if you measure any spot, the spectra is always actually insulating, and it shows actually 0 density of states at EF. That means on the full images are actually insulating images. Whereas we have actually done the similar for the 0.7 and 0.8. 0.7 should have actually 70% metallic character and 30% insulating character. But this gives actually fully metallic density of states in the EF. So that means the sample is fully metallic throughout the sample. So our conclusion is our investigations within the experimental limit reveals that embedded microscopic inhomogeneities do not exist in the insulating as well as in the metallic region. So this discards your population theory in context of NXWO3. Now these another 3 models now exist. We have to see which one fits best to explain our metal-insulator transition. So let's actually let me touch actually the metallic samples, and this is the mainly the valency band spectra. And as soon as we are trying to understand the metal-insulator transition, but when we are studying MIT, there are many other aspects of the there are many other things comes up, and we also study them. And our conclusions are we have actually studied many aspects of these samples, and I'll actually go one by one what are those and how we solve those issues. And this gives actually a 0.58 and 7 and 8. And you can see, and this gamma is actually the center of the brilliant zone, and M is the extreme point of the brilliant zone. And a very simple band structure says that the valency band is up to 3 electron volt, and the conduction band lies up to 1.0 electron volt, and there is a 2 eV complete band gap for any doping. That gives actually the high band gap of the WO3. As I have already explained that if you put sodium, the sodium 3s is going to that 5D and the system becomes metallic, and you put more sodium, more electron will go to 5D and the EF will slowly go up. That is actually according to the rigid band model. But we are not sure that whether the rigid band model is actually can be applicable to sodium tungsten bronze or not. People say that rigid band model can be applied, just that is the assumption, but we would like to prove that whether rigid band is a failure or is a success, whether we can assume rigid band model or not. So to do that thing, I have taken actually spectra of the of gamma point of each sample, and then this we have actually compared starting from the EF. You can see as soon in the rigid band model calculation, as soon as you put actually sodium concentration, your EF increases, EF shifts, and this is the shifting amount you can see. And we'll see actually in our experimentally the 4.5 eV peak, which is very sharp peak, we can actually take this as a crosser, and we can measure the shift between the 0.8 and the 0.58, and experimentally we found that it is the 0.24 electron volt, whereas the rigid band model says that it should be around 0.3 electron volt. So our conclusion is actually a rigid band shift can well explain the band structure with respect to in sodium doping in the purely in the metallic region. This is one issue which actually we concluded that rigid shift of band is actually applicable. Now we have actually mapped the band structure and overlapped with the band calculations, and this is the rigid shift can actually well explain those things. And you can see that these are, there is a yellow bright band in the gamma point, which is actually artifact because when we clip the electron scatter from the steps, and those momentum can have actually zero momentum, and they reflect actually around the gamma point. So this spectra intensity is coming actually because of this high intense band density of states from the M point. So let's go to the very low energy spectra of the near, and you can see the band is actually moving from the it's from here and making a electron type band, and we don't see actually any impurity band. Just like in the semiconductor with a electron dope material, it gives actually impurity bands. We don't see any in sodium induced impurity band. So by that way, we discard the formation of the impurity band in this system. So it only actually gives actually electron-like band, parabolic band, and the bottom of the conduction band shifts with the X, and there is no sodium-induced band. So here I'll actually show another model in the 79. IISER and Arnav actually proposed that in a pure metallic, you know that is the density. If your metal, if you put it is actually digital metal, then your density of states around your EF will have actually a cups-like structure, and otherwise, if you take actually, let's take actually gold. The gold spectra will be like completely like this and fall in the EF at 0 Kelvin. And if you take actually in a high temperature, there will be a little bit dip, and those density of states will go to the higher binding energy because of the Fermi distribution. But in sodium tungsten bonds, and if you do actually if you measure and you see that there is a corpse-like structure even at the very low temperature. That is because actually this is actually no more actually a very good metal, and this is a disorder metal, and in the disorder metal the density of states will vary as actually e to the power half. And because this is actually when the electron is actually moving, it can actually interference, and it can actually scatter from the sodium sides. That gives actually pseudo gap type of feature at the EF, and just that corpse-like structure develops. And this actually once again actually validate this IISER and ONF model. Yeah, so now actually we discussed this impurity band. Now we have actually left with the mode transition and the Anderson localization. So mode transition is actually very less likely because the tungsten 5D is actually quite large, and for any amount of sodium doping, that means even if it is the 2.5 fraction of percentage of the sodium doping, this is actually still insulating. The mode transition should be valid when the X has to be integral, so that only the band has to be half filled, then only mode criteria will be applicable. Or if you even if you actually take actually your 5D as the orbital way, so for only 10% of the doping, that means because if the 5D can actually have a 5D can have D have actually 10 electron, and this for a 10% of the electron, that means 0.1% of the electron, that which is actually sodium 10%, sodium 0.1, the system should behave like an insulator, and for a less than 0.1 to 0, the system should be metallic. That means for the integral doping, the system should be metallic. So mode transition is not actually favorable in this sodium tungsten bond. So it is the Anderson localized which is actually preferable. You have actually a density, you have a critical edge of the doping, and below all these states are actually below the mobility edge. All these states are localized, and these are non-localized states. EF can move from the WO3 to slowly with the electron doping of the sodium doping, and as soon as it crosses your mobility edge, you are actually seeing the metallic sample, metallicity in the sample. But this Anderson localization can actually have lot of consequences, and see actually what are the consequences. See, and we have also measured actually the effective mass in the metallic sample, and which is actually increases with X linearly, and which is well matching with the other experiments. So now we have actually measured in the metallic Fermi surface. They are actually quite well excellent matching with the different X values, and you can see this is the band structure calculated Fermi surface. There is no Fermi surface in the X point or M points, so it is the bulk Fermi surface. But if we measure actually the insulating one, insulating should show actually a Fermi surface around gamma point, not at X point, but X or M point. But insulating feature shows actually Fermi surface in X and M point. So it's possible that these are the surface reconstruction, but we don't see any surface reconstruction at this energy. So we would like to actually see surface sensitivity of metallic sample with photon energy. So what does it mean? So you can actually probe a metallic sample, a sample, the surface and the bulk. How you can surface? So this is called the universal curve. This is the universal curve. If you choose your incident photon energy lower than the, let's say maybe 50, then you go less energy, this will become actually more bulk sensitive. You go towards 50 energy, it will become surface. So this type of surface and bulk photon spectra you can map by tuning this photon energy. And this is only possible in the synchrotron, and we are heavily dependent upon the synchrotron radiations, and we have actually measured almost all measurements are actually synchrotron based experiments. So based on that one, we have measured this Fermi surface in various photon energy, starting from the 21, which is the helium 1 alpha line in the laboratory energy, which is coming from the helium source. And in the synchrotron, we have actually measured up to 42. 42 is actually surface sensitive. So let's see actually how it look like. And if you take a 26, you still don't see any Fermi surface around MR point. But if you see a 42, which is surface, you can see in the gamma, in the X point, the Fermi surface is appearing. What does it mean? That means in the bulk, you have a undistorted cubic structure, and this is the cubic structure. But in the surface, you have a distorted octahedral, WO6 octahedral, which makes this as a distorted perovskite type of structure. And as a result, your A and your B becomes actually double. That makes actually your this X point becomes actually the new gamma point. That's why the Fermi surface is actually duplicating in the X and M point. And this distortion of the WO6 octahedra is because of the deformation of the individual WO6 octahedra, and displacement of the tungsten form is actually central position in the surface only. But the bulk is actually very much actually undistorted cubic structure. So now, we have to study we have to see actually whether the Anderson localization and its consequences, and we have to go into the insulating sample. So we have actually measured the insulating sample, and this is actually for students. This is actually your this is your gamma to X in the brilliant zone. If this is the crystal structure, you have actually gamma to X direction, and is the gamma to M direction is this line, and we have measured from the top. So this plane is measured, and for the gamma, when I will write, this is the gamma M and Rx plane we measure. So this is the valency band, and this is the measurement of the valency band band mapping, and you can see clearly you have a Fermi surface is appearing at the M point, and also a new band is actually appearing around 2.5 keys, which is not actually calculated by, it is not actually predicted in the band calculation. This is actually very worrisome, that why actually it is actually appearing. So to understand these things, we have actually we have actually measured in the low near EF spectra, and which only shows actually a 5D character of the tungsten, but this band is never actually crossing the EF, making it actually insulating. So our conclusion is actually because of the Anderson localization, though the strong localization is not too strong to destroy this dispersion, but it has actually and all these states are actually almost actually localized, and as a result, you have actually a Coulomb gap, a soft Coulomb gap is actually originating at the EF, and as soon as you go little bit away from the EF, your density of states evolves, whether it's actually Coulomb gap or is a non-Coulomb gap. And Coulomb gap is only actually develops when there is a long range Coulomb interaction, and that can be tested if you actually feed the density of states with actually e to the power a alpha, and if your alpha is actually with 2, then we can say that it's actually Coulombic type. So if our fitting says that it's actually close to 2, so we say that this is actually a soft Coulomb gap arises. Soft because actually your EF has actually zero density of states, and as soon as you go little bit lower than the EF, your density of states arises. So in if you say there is a Israel group actually claimed in 1999 that in the sodium tungsten bronze you can see a surface superconductivity at 91 Kelvin. And so how to then, because we learned that with a different photon energy, you can tune a bulk and a surface electronic structure. So we measured in at two different this spectra we have taken at 130 Kelvin and also at 42 eV, and we didn't see any quasi-particle at EF. So we discard that this claim has no validity, that it has actually any superconductivity. So sodium tungsten bonds is not actually showing any superconductivity. So at so high temperature, we have actually checked the surface electronic structure and the bulk electronic structure. So there is no quasi-particle feature at EF. We discard their claim. So this is actually your parabolic band without your Coulomb's gap is overlapping with the sodium WO3, and we have actually different the same replica of the Fermi surface. You can see parabolic one. So this shows actually a electron-like pockets and X and M points. So whether this is actually surface reconstruction or not, to understand this thing, we have done actually surface sensitive lead, which shows a very well 2x2 surface structure. Lead is very much surface sensitive, and this gives actually idea that it can actually generate X and N point with a new gamma point. And as a result, Fermi surface mapping also give actually a Fermi surface mapping give us a Fermi surface at N and X point. Since as I am saying that this this point 0 to 5% doping is actually insulating. So an insulating sample does not have actually Fermi surface. So a new terminology we introduced, which is called remnant Fermi surface. What does it mean? So suppose if I switch off the Anderson localization, the system is metallic, and if the system is metallic, how the Fermi surface should look like? The insulating feature keeps that Fermi inside it, and if you take a density of states little bit away from the EF, your Fermi surface will be similar to the exactly if there is no Anderson localization. So remnant Fermi surface, it says that it has the Fermi surface in X, M, and gamma point, which is because of the surface reconstruction. So now I'll actually go for the temperature dependent of photoemission spectra in this insulating. So each spectra is taken around gamma point. So what we thought that let's do actually without knowing, let's do actually a series of temperature based from 50 to, because this is sample is insulating, we cannot go very low temperature. So we started from 50 to 270 to see actually whether actually you see any different feature or not. Is there actually any new feature or not? Surprisingly, we see that the density of states at 2.5 PB just vanishes at 230 Kelvin. That actually indicates us that there is a possible that polaron formation, that when you increase the temperature beyond 230, the polaron, that electron, polaron is actually nothing but this, the electron given by the sodium, and it is actually dressed the phonon and the lattice. And that polaron no more actually at site, and it is so the density of states all about the brilliant zone. no more actually gamma sensor. So if so most of the will arises at gamma, and in the polar formation temperature. Above the polar formation, the densities of states should spread zone. To justify this, to do a special type of experiment with a special which actually acceptance at a small medium angle and a wide angle, so that it can take most of the billion density of states around gamma position. We measured mode direction and integrated them for only the gamma around the gamma position. Your density of states not for the low temperature to the high temperature. In the low temperature, the density from this region to that region, whereas in the if you integrate whole over the Brilliant zone for a wider angle, the density of state variation is quite low. Yes. So 2.5 eV peak variation with temperature gives signature of polar information at the valency band H, and this is the 13% of the Brilliant zone integration, whereas the 30% and the 55% Brilliant zone. So a wider integration gives actually no variation on the density of states over the temperature, whereas a 13% Brilliant zone integration gives actually a high density of states difference between the high temperature and the low temperature. So we conclude that the density of states at the valency band is gradually decreases around the gamma point and increases at other k points with increasing temperature. So is there any or lattice deformation around 230, around this 230 whether there is any lattice deformation at 230 temperature of this sample, so that Polaron will be favorable. To understand these things, we have to do a low temperature XRD, and we collaborated with Gautam, and we measured from the 9 Kelvin to 300 Kelvin, and we exactly found that at 230 Kelvin there is a new peak is actually developing in the XRD spectra, and this shows that that WSX is actually gets significantly distorted at the low temperature, and distortion occurs below 230, which induces Polaron formation.
Satyabrata, can I ask a question?
Yes, sure.
Siddharth here.
Yeah.
Hi. Have you guys checked any Raman signals to see whether this thing also happens? Because surely some mode will some Raman mode will go soft.
Right? So I tried, and this is I think the fluorescence is too high that to capture actually any because the you see that only the octahedra is actually rotating. It should reflect.
Right.
We tried because the sample surface is actually not. I don't know how to handle that surface because the fluorescence is quite high. So to suppress fluorescence, I think Gautam can suggest what to do. But the fluorescence was quite high to find out whether actually at this temperature there is no temperature. You have to do actually temperature dependent Raman. It is not the room temperature will be helpful.
Right.
So we have not done actually a temperature dependent Raman. That we can do sometimes maybe.
Sure, because that will, if you see it, that'll help your cause in a big way.
Yeah. That will be our next paper definitely. So so now actually I'll go for a. So this is all about the three-dimensional system. Now I'll go for a very quickly for a two-dimensional system, which actually.
Satyabrata, I had one more question before you go to the two-dimensional system. I just wanted to take you back. If another smoking gun signature that you could look for is the following. See, since you're guessing that Anderson localization is very important for this metal insulator transition, then let's say you're sitting in the metallic side. Let's say you're sitting at 0.8 doping, right? Then you could try looking at transport signatures like magnetoresistance, because weak localization probably will be very important for the metallic side.
Okay. So let me quickly go. What you are saying is right. So what you are saying, we have done. If you see, So here, we try to understand whether it's actually weak localization or strong localization. A weak localization should show you a insulating feature in the low temperature, and there metal to insulator transition along a temperature line. That we don't see. So metal.
No, but you can look for magnetic field dependence, in the sense that and you're looking. This slide is showing us data deeply in the insulating side. My claim is that if you were to look in the metallic samples, right? If you look for transport signatures like magnetoresistance, like magnetic field dependence, then there is a chance that you might actually see the destruction of weak localization.
But metallic is actually a very metallic is only because these are actually digital metal. So still, I don't think that weak localization you can capture, because the quantum interference will actually destroy because of this digitedness, right?
No, Satyabrata, the weak localization signatures have to be seen on the metallic side, because once you're on the insulating side, most likely you will hit the strong localization regime, and it'll be very hard to see the formation of those loops. So if I'm not wrong, the better way to see it will be with, let's say, 0.58 doping, 0.7 doping, and to come down in temperature, low temperature. You'd have to look at low temperature magnetoresistance, and there is a chance that you might actually see that as you crank up a magnetic field, then the magnetoresistance will fall.
Okay. That we have not tested. Magnetoresistance we have not done. Only resistivity we have done. That is actually not showing anything. When say in metallic, it is actually just a metallic.
Well, the magnetoresistance is one of the smoking gun signatures to look for weak localization.
That we can explore. Good point. Well taken. So should I move?
Yes, please carry on.
So I'll actually move now to the two-dimensional system, and in the two-dimensional means it is not the crystal structure which is actually two-dimensional. Okay, let me go. Then this will actually Pell's transition, or this charge density wave transition. So this I'll talk about the phosphate tungsten bonds. Phosphate tungsten bonds can actually exist in many. This M can be actually, because this M we can take many number. So these are the slabs running in the zigzag fashion. And what does it mean actually by two-dimensional system? Its crystal structure is three-dimensional, whereas the electronic structure along the Z direction is not dispersive. That means the electron is actually moving in the 2D plane. It has zero dispersion along the Z direction, and the layers are actually attached by a van der Waals force. So with this one, you can actually these are the crystal structure generally. I'll not actually go, and I will actually do a transport phenomena. When you do a transport, you see that there is actually two humps at 114 Kelvin, and another actually there is a dip in the 114 and 60 Kelvin. So that actually gives actually indication why there is actually humps in the or anomalies in the transport phenomena. In the transport, though the gross transport phenomena says that it is metallic, but there is anomalies in the transport. So we thought that this will be actually charge density wave, because this P4 O12 and O44 is actually similar to 4 times of the gamma MO4 O11 4 unit of this type of cell, which is this system shows charge density wave. So we thought that this is actually a charge density wave and wave material, and we have actually tried to understand this. So what is actually charge density wave? Let's actually understand this is. So you have actually, let's take actually a chain separated by A, and because of the, if you lower the, and your density of states is actually quite flat. If you plot actually your band structure, you have a parabolic band, and let's assume actually you have actually a KF point here, band crossing at the EF. So now, because of the lowering the temperature, so there is a electronic and your crystal energy, lattice energy competition, and to stabilize it, that one lattice point will move towards another and make actually a two-way periodicity. Then what happens? Your density of states or the charge density becomes actually a wave. So that is why it is called a charge density wave. Then what will happen? So you have now this will become, if your lattice become actually new lattice, your new lattice lattice construct become 2A, and if your KF is just half of your pi by A, then your new Brilliant zone will become actually reduced to half. So as a result, you will open up a band gap at the new zone boundary. And the system will go to a insulating phase. That is the charge density wave. So this is become actually new zone boundary, and you have actually now gap at the new zone boundary, and the system becomes actually insulated. And what is the signature? And you can actually see the backfolding of the band, and which can have actually very less intensity. So what is this consequence? When in the metallic 1D Fermi surface, you have a straight line in the metallic state. When there is a charge density wave, your Fermi surface will vanish. So to say anything regarding the CDW, the Fermi surface mapping is actually very important, and your nesting, this Q is called actually the nesting vector from one part of the Fermi surface to another part of the Fermi surface, and thus this Q should match with the CDW scattering Q vector from the scattering experiment. So this RPS is actually very helpful to understand the band, not only the band structure and the Fermi surface, even in the three-dimensional Fermi surface, and you can actually map the surface Fermi surface and the bulk Fermi surface by tuning the photon energy. And if you do actually a Google search about this RPS, then you can see there are a lot of activities in the last 2 decades. And IISER has actually made this RPS as one of the benchmark tool to understand the high temperature superconductivity. And I think Siddharth can talk much more on the IISER. They have actually done a lot of work on the theoretical part on the IISER work. And for the last 1 decade, Pnictites actually had taken over the RPS. And for the last few years, it is the topological insulators. So you give a search and you see that all this nature PRL papers are actually full of RPS activities in the journals. So I have taken actually a band calculation, a pseudopotential calculation for this system, and because of this 2 layer, and this is 1 layer and this is another, there you can see actually in the calculation picked up actually the bilayer splitting. And along the gamma j direction, you can see that very less dispersion. There is no dispersion along the gamma j. So that is why these are actually 2-dimensional system. So this gives actually, these are the valency band spectra in the above this anomaly temperature. And we have actually measured and overlapped with the calculations. These are not important. And we have actually calculated the Fermi surface, and you can see the Fermi surface is very much actually straight, no dispersion along the gamma z direction. That gives actually because of the two-dimensional nature, and that's why we have actually overlapped. We have actually taken the projection on the two-dimensional Fermi surface, and this is the two-dimensional Fermi surface, and RPS actually maps the two-dimensional Fermi surface. And to have a charge density wave, the Fermi surface should have actually a very straight patch which should be connected by a nesting vector. So now we calculated, we measured actually Fermi surface in two temperature. And 140 is the above CDW temperature, and at 20 Kelvin at the less than the lower anomaly temperature. And you can see there are differences in the intensity between two Fermi surfaces. And if I take this gamma point as a normalization factor, then you see, and both are actually overlapped with the Fermi surface, a two-dimensional Fermi surface, and matches quite well. And now we have taken the charge density wave from the scattering experiment. This Q vectors, these are Q1 and Q2 because of the two anomaly, and we have matched with the straight patch, and we can see that in the low temperature, those patches are actually reduced density of states. That means those patches, these are the Q vector, Q2 and Q1 removes actually density of states from this patch of the Fermi surface. That increases, that gives actually your okay. So to understand actually how much actually density of states is removed, we have taken a cut in the in this direction, because the gamma, this gamma Fermi surface at the small Fermi surface is not taking part in any nesting of the Fermi surface. Only these patches, this straight patch are actually taking part in the nesting of the Fermi surface. This Fermi surface is intact in low temperature and high temperature. So we have taken actually along this direction and try to understand what is the reduction in the density of states. So we have taken actually two band structure and measured its density of states, and you can see at gamma A, B, and C point the red line is the 140. 140 you have a similar density of states in all Fermi surface points, Fermi surface cave points, whereas in the low temperature you have a very much reduced density of states. This shows that you have a due to the partial nesting, due to the imperfect nesting, density of states reduces in the partially nested region below CDW temperature. As a result, conductivity decreases and shows anomaly in the transport measurements. So this is actually our summary, that this is the nesting which actually responsible for the CDW nesting and removes the density of states from the Fermi surface. That's why you see actually reduced density of states, and the transport phenomena also, because that's why the resistivity increases, then once again it decreases because of the gross metallicity of the system. So that is actually, I would like to thank you all of you for attending. So of course I have completed my answer. Yeah.
Satyabrata, can you hear me?
Yeah. Siddharth, I can hear you.
So I guess Bhartosh would have, I think he's having some trouble with his microphone.
Yeah.
Speakers. So anyway, I'll go ahead and ask a question.
Sure.
So in this system that you're studying, this beautiful sharp drop in the density of states between A and B, right? That last curve that you were showing.
Yeah.
So this this you're saying coincides with the anomaly, is it? The transport anomaly?
Yeah. No. B is actually, this gives actually, you see,
this will lead to the gapping out, right?
Exactly.
Right. So my question was, is there any chance of any magnetic phenomenon also occurring out there? Sometimes, for instance, I mean, people say that Slater antiferromagnetism can appear because of nesting and stuff like that. So is there any chance that you can also have some SDW physics?
From photo emission point of view, you cannot put any magnetic field because it will destroy your momentum.
Sure.
So other type of experiment has to be done. So
I mean, neutron or something.
Exactly.
Could you check? Maybe there is a. I don't know. I mean, is there some chance that you could get some kind of
neutron? We can do, but the one technical problem is actually this. Let me tell you. Actually, I have not talked about how we do experiment. These samples are actually 300 micron. Neutron asks for you a lot of sample.
Okay.
So that is one issue, because these are 300 micron is a dot. And you cleave actually 30 sample, you get actually lucky if you are actually getting actually one clean sample. So that is not very easy to actually do the experiment.
So what about ESR or NMR, where you can look for a magnetic moment, basically the formation of some magnetic moment?
Yeah, that can be done. That I have not done, definitely. So I can explore.
Yeah, I mean, I'm just wondering. Because I'm just wondering, is it possible that you could see signatures of some kind of incommensurate structure, magnetic structure happening, coinciding with all of this?
Yeah, it is possible, and maybe a susceptibility can give you, but I have not done, because that needs actually a lot of sample rather than a small sample. We cannot do.
Sure.
So that is possible.
Okay, thanks.
Yeah.
So any other questions, comments?
Yeah, Bhaktos, now you are audible.
Sorry, it was just got blocked somehow.
Okay.
Yeah. So does anybody have?
Okay. Can I ask?
Yeah.
So you said that you have with low energy. I just missed it. With low energy probe, you can see the bulk, and with high energy probe, it's a surface. I mean, it's not very clear how.
Okay. So okay, I can tell you. Sorry. Let's see here. I'm sorry. Where it has gone? Just a minute. Let me see where. Yeah. So you see, you have a universal curve. What does it mean? Suppose let's divide this curve in two parts. Around 50, above 50, less than below 50. If you increase the incident energy, so it will penetrate more to the sample, and your electron will have a more kinetic energy to come from the inside. So this is more toward actually. If you increase the more energy, it will become that. Suppose you have 1000 TeV or 2000 electron volt photon energy, it will be actually the electron will come from the bulk. So, and if you take actually 50, your escape depth is actually very low. Only 5 angstrom escape depth. So that means it is coming from the surface. If you increase more energy, it is coming from the 30. That is the. Yes. Is it clear?
No. Now I got it.
Any other questions?
Bhavtosh, I had one more question.
Of course.
If I may ask. Yeah. Sorry, Satyabrata, just one more question. In the 2D sample where you see the nesting physics, are you suspecting that phonons are important there as well?
Of course, there must be.
So you're saying that it's a piles like dimerization.
Yeah.
So then, have you again looked for any other measurements which can back this up?
No. We can do. Luckily, we have only the sample. The world, nobody has the sample, so we can do it. So time is not a very critical for us for this type of sample.
Okay.
Yeah, we should try again because we were trying once and there was some issue with I think.
I think we
should actually try.
We can try actually.
Again.
We have samples, so we can try that thing.
Will Raman give some signature at low temperature?
I tried actually. It was so small. We can do. I have not done actually because I was actually waiting for the. If temperature dependent can be done, then it's the best. Because you have to do it actually in at least in these two temperature. In these two, at least below 60 you have to do, and above 114, so that one nesting vector will be here, another nesting vector will be here.
You can do that.
Yeah. Most of the thing, if the fluorescence is high, then it spoils. That is the thing. It's very
So if the fluorescence high, what is the band gap of this sample? You said again?
No. It is there is no band gap. It's actually metallic. Only the anomaly. Yeah. That is the problem.
One can try with
If
near I or
yeah. Yeah.
See. Okay. Let us. Yeah.
Okay, so I think we can formally close, and if people want to hang on for discussion, I guess that is, of course, possible. No, and we'll formally close. Yeah. So thanks, Satyabrata.
Thank you, for giving me a chance to.
No, thanks.
Thanks, Satyabrata.
Yeah, thank you.
Yeah. Good.
Good talk.